Okay, so I switch on the record and okay, so let's start first of all about the power system, power network. And let's start with power system. Just to put in a Google name power systems, I think we'll get, okay. Okay, United Power System. Just to have a good screen. Okay, it's a brand. United. Then we will write a short version. Okay, let's start with this. For example, this screen to be easier to discuss. It's from a Wikipedia. Okay. Of course, we will talk about the Europe and European power network first of all, because because we are in Europe and our subject is all about the Europe and all about the Latvia. What is the border of Latvia? Okay, so first of all, what is a power network? What is a power system? We know there are a lot of power system elements, such as generators, transformers, transmission lines, distribution lines, and at the end, consumer. Yes?
Consumer, yeah.
Yeah. So all of these together makes the power system. But how all these units could operate all together at once? This is the main question, what we are going to discuss. As I mentioned previously, there is a very ancient law for a power balance, like the mechanical power is equal to electrical power plus losses. I can power balance equation. Power balance, what is power balance equation? Okay. Oh, no, electrical. Oh. Okay, I use paint and write by myself.
Yeah.
This will be easier. So this is a very ancient equation because for now, maybe it's a little bit different because from ancient time, all the produced electricity was from a mechanical energy. For now, for example, solar panels, we don't see really any mechanical actions. Yes, it's an electronic flow of electrons. Yes, so but we will use a standard formula from Pm mechanical here equal with P electrical plus P losses. So this means that at each moment of time, any moment of time, we should produce mechanical energy, which we transform to electrical energy, plus all the losses. Yes, and because losses is waste energy that consumers can obtain, can consume. So in this case, we could talk about this distributed or concentrated and power system. This is more about like a modeling, how we could imagine our power network, how we could simplify our power network, yes, power system to analyze. And in this case, for example, we could return to our, where is my screen? Power balance. Okay, to this, yes, to this screen about the power system. So it means that in each time moment, yes, the production of electricity is equal as it is in equation. But there is a question, where is the border for this equation? Where is the where is this area where this equation is true? How to define this area? And in this case, we defined the area with the same rules, and this area we call power network, power system, united power system. And in Europe, in this screen, we could image several power networks. In this case, we have the Central European network that is called UCTE. We have Nordic, Great Britain, and Baltic.
Baltic.
Yeah, for Baltic, this image is a little bit not true, because our power network was developed in Soviet times. And in this case, we, for now, we still are a part of West Soviet Union power network. In this case, for Baltic power system, there are additional countries such as Belarus and Russia. This in this region, with the biggest city of this region was St. Petersburg, which includes in this area. Why? Why this is such important? I'll try to explain. To make this power system united, it means that we should to collect all the elements to one network. For example, okay, we have one power station, power generator, yes? We run power generator with a power, for example, of 100 megawatts. In this case, we could connect to this power generator the number of consumers of a total power with the same, okay, plus losses, for example, so 5 megawatts, for example, losses, so it means that we could connect 95 megawatts of consumers. Is it clear?
Yeah.
So if we have two generators with a total power of 200, it means that we could increase the number of consumers twice. And in this case, okay, we have one generator, we have a connected consumers. Now we started to run one more generator. How could we add this? Okay, one generator plus consumers, this is a small network. How we could add one more generator to this existing network? It means that we need to synchronize one more generator to the existing network. What does it mean, synchronize? In this case, we need to run the electrical generator like an electrical machine with the electromotive force of this generator, this vector, to be equal to the first generator with the angle and frequency. So I can try to make a short, for example, this is the electromotive force of the first generator. If we know, this vector is moving one, it is rotating clockwise for each generator. And if we have two generators, it means that we have for each generator this electromotive force, yes, which is rotating. So if we want to connect this one generator to the existing system, we need to switch this generator to our small power system in a time moment when these two vectors are equal with an angle and the frequency, because frequency, how the speed of rotation, yes, it is a frequency. Yeah. So the frequency should be the same, and the angle of this vector should be the same as well. Of course, there is a possible deviation, but all the deviation, yes, between these two vectors, yes, for example, if we have connection in time moment, then there is an angle phi between these two vectors, yes. We'll proceed a new voltage here. And as a result, a force current. Which one is dangerous for the power network elements? because it could destroy some elements such as generators, transformers, and so on. So that means that if we want to synchronize one more generator to the existing one, we need a special automatic to synchronize the generator to the existing one. So the strategy how we make a power system starts from a first generator, and all others are synchronized to the first one. And all these synchronized generators make the power system. And for each power system, there are special rules. And for example, if we see what to this scheme, we can conclude that all the units here are synchronous. All the units here are synchronous, but units here and here are not synchronous. The frequency is the same, but the period is different. And in this case, we can connect this power network to this power network just with a simple line, because they are not synchronous. And what for about the Baltic power system? So yes, it was developed, as I said, in Soviet time. So, and the first generator, this is the first one, when this collection starts, yes, was the Volga River hydropower plants. Very powerful river with very powerful hydropower plants.
Okay.
And they based on the type of the hydropower plant. Yes, the hydropower plant is very
take one.
No, sorry. I'm trying to find the words. Just very flexible. Hydropower plant is very flexible because the production of electricity depends on the water flow, and we could decrease or increase power flow very quickly, very fast, and with a large amount, which is impossible for all other types of power generation. For example, we have, if we structure the types of power generation, yeah, what types do we have? We have nuclear power generation. Nuclear is not flexible because it depends, yes, on the power from the nuclear reactor. Yes, okay, of course it produces steam rotates steam turbine, and steam turbine rotates the generator, but the energy from this heat energy, yeah, from the nuclear reactor, yes, it is not flexible, very not flexible. It's a problem, yeah, to make the output power from a nuclear generator. Yes, from all the wind, solar, and so on, they are not predictable, and they are not flexible at all. Yeah, and the next
open season.
Yeah, is the thermal power plant, CHPP. Yeah, when we use fossil fuel, yeah, to produce steam. Okay, there are two types of turbines in CHPP. If you use, for example, gas as initial energy source, yes, so we have a gas turbine and we have a steam turbine. So we fire gas, we rotate gas turbine. The gas turbine rotates a generator, we produce electricity. The heat from this burning of the gas, yeah, produce steam as well, and the steam rotates steam turbine, and steam turbine rotates the generator. So we have two types of turbine and two types of generator. Okay. Yeah, in each CHPP. So we call this type of generator like a turbo generator. So we have hydro generators, we have turbo generators, and all the renewables. we could say that we have three types for now, because the nuclear as well steam turbine, so the system steam turbine and power generator is the same as for if we burn the fossil fuels. So three types, and the main, of course, there are only two types, because the amount of renewable energy is still very small for the old generation. Yes, so we have main two types of generators: hydro generators and turbo generators. And turbo generators, they are not flexible. Okay, nuclear are not flexible at all, but for CHPP, their flexibility depends on the steam production of type, how much we could produce the steam, because the amount of steam, yes, is our flexibility. If we have a big, how to say, like a boiler, a storage of steam, yes, we have more flexibility for each moment. If we have small this steam storage, we have less flexibility. But in any case, this flexibility is limited. But for HES, it is huge, because if we have a lot of water, yeah, we have a lot of flexibility for a hydropower. And this means that in each, we could use these hydropower plants for balancing the power system very well. And all this West Soviet Union power network was made based on this Volga River hydropower plants. And no, okay, if we listen, for example, our technical guys from our utility company, such as Latvenergo, they could say that our Latvian, Baltic Power Network is one of the most reliable power network in the world. So it was developed with a huge reliability reserve in 50s, 60s years of 20th century, 21st century, sorry. So in this case, we could understand that we have the first main generator, and all others are synchronized to this one. Next, we will discuss about the future of Latvian power network and the details, because in the year 2025, we are going to desynchronize with Russia and to synchronize to the Central European this network. This is a step that will be in the year 2025. But this is a political decision, because as you know, Latvia is independent from the 90s. It's more than 30 years for now. But all the, how to say, engineers, yes, are maybe I'll find better sentence. Okay, the engineers from the dispatch center, from this transmission network, and from the Latvenergo, the utility company, yes, still was very satisfied with this power system, because it is, as I said, very reliable, yes, and we don't need to pay nothing for this reliability and balancing. So this was very feasible for us, but the political decision, yes, to desynchronize with Russia and to synchronize to the Central European network, and this is quite challenging. And nobody knows what will be in the year 2025, to tell the truth, because this synchronization is quite complicated, and I'll describe why. First of all, let's talk about the next power network, this power system, about the Central European. The Central European power system is quite huge, and in this case, it contains a lot of different countries. And in this case, it is impossible to make the first generator. Which one will be the first, and all others that are synchronized to this one? In this case, each country follows special rules for the connection to the Central European system. And each country participates in such a task like a frequency regulation. So there are special rules how each country with its, how to say, local power network, yes, could be a part of this huge Central European power network. For the smallest power network, like for example Nordic, yes, or United Kingdom, all that I said for the existing Latvian power network with this part Russia and Belarus is true, yes. But when we have so huge power network, yes, with a lot of different countries, yes, this is quite complicated to make this type of power network. That's why for the huge power network there's different rules. But we don't waste time just to see this, how to say, nuance for this network. Just you to have this, how to say, overview of the existing system. Okay, yes. For now, we are going, these 3 Baltic countries are going to be synchronous with the CPE, yeah, Central Power Network. Why? Well, first of all, if we see the map, where, okay, if we disconnect to Russia, where we could connect, first of all, we have at the north Nordic power network and the south Central European. So we have only 2 possibilities to connect. But how to connect, for example, to the central, for the Nordic system, because there is a Baltic Sea. And if we have a Baltic Sea, we can't make, how to say, transmission line, yeah? So we need only what we could do, it's underwater cables, yeah? And for now, we have existing underwater cables, but they are not AC, they're DC, connected from the Estonia to Finland and from the Sweden to Lithuania.
Why? What purpose we are connecting DC? We are getting DC.
Okay, very simple, very good question. But okay, I just switched the page to this ASTM. This is our transmission operator for Latvia, and this is the English version of their homepage. And there is a transmission network. We could see the state of Baltic Nordic power system, yeah. And here we could see for now the DC cables, Finland to Estonia, and the power for now. And this the second one, cable from Sweden to Lithuania with the power. So flow direction and the power. Yeah. So your question is why we have the DC? No, because these cables are not new. They're, how to say, built several years ago, and Nordic power system is not synchronous with Latvian, Russian, and Belarusian power system. And if we want to connect 2 different power systems, yeah, how we could do this? Because they are not synchronous. They have this angle between these concentrated ideas. If we, okay, for a power system, we could discuss about the system using such a definition like a concentrated power network. What does it mean? This means that we could represent all the power generators in one power system like a one big generator, because they are all they are synchronous. So they concentrate, unite to a one huge generator, yes? So, come back. This generator is not synchronous to this generator. And we can't synchronize them because they're 2 separate power systems. In this case, how we could connect these 2 power systems? This is actual for every region, for every power network in every world's region. In this case, the best solution is to use DC cables. Why? Because for DC cable, we have at each end of this DC cable the electronic device that transform AC to DC, transmit the power to the second end, and transform the DC again to AC. But this AC is one end is synchronous to this system, and the second end is synchronous to this system. Very easy. For example, Japanese power system is very interesting because, as you know, Japanese are islands.
Yeah.
A lot of islands. No, we 3 biggest islands. Yes, yeah. And in the beginning of the, okay, not beginning, at the end of the 19th century, Japan was a really close country. And two countries like a United Kingdom and United States of America started to come to Japan with their technologies. And United Kingdom system was with a frequency of 50 hertz. But for United States of America, the frequency was 60 hertz. In this case, historically, part of Japan have a power network with a frequency of 50 hertz, and part of Japan has the frequency of 60 hertz. And for now, for modern Japan, there was a question what to do, because we have two parts with different frequency, and they just decided to connect these two parts using DC cables, not to rebuild, because you understand, to rebuild this power network, it's huge expenses. Much easier to connect these two parts using the DC cables. So this is solution, how to say, could be for the one country, very actual. In this case, yes, how we could connect different power systems of different parts of the system. Yeah, so yeah, just lost my idea. Yeah, this is UCT. Yeah, about the Latvia. Okay, yeah, we discussed about the where we could connect. Yes, we could connect the two possibilities to connect to the central and to the Nordic. In this case, if we can, if the political decision could be to connect to the Nordic, it means that all the connection could be through the Estonia, because this is north,
Near to.
the north country. Yeah, if we connect to the Central Union, it means that we connect through the Lithuania, and win. Okay, win, not win, but won the solution to connect from the Lithuania to the Central Union, but it is not a technical decision, it's a political decision.
Yeah.
Now let's talk about the advantages and disadvantages of this solution, this decision. First of all, we need to understand that for all the three countries, Baltic states, we have a deficit of power generation. We could produce not enough electricity for our use. The best situation is in Estonia, because they have their own fossil fuel, fossil resource. It's not as, I forgot how it is in English. I need to translate. Okay, Latvia. Wait, just forgot. Where is Latvian? Okay. It's a flint.
Flint.
Yeah. It's not a coal, but it is very similar to coal. It's a flint. And they have 5 power CHPP here in this region border to Russia, when they could use their own fossil fuel to produce. So, but there is, how to say, a green politic in Europe, and all such CHPP types that use, for example, coal and something similar to coal, they produce a lot of CO emission. And this emission is very harmful to our futures, this is green politic. And there was a decision several years ago, I think the beginning of this was something in the year 2019, then the European Council increased several times the fee for CO emission. And from the year of 2019, Estonia shut down their own CHPPs, because in the market condition, okay, you have very cheap fuel, but when you add fee, no, like a tax, it's more not a fee, like it's more like a tax, yes, for the CO2 emission to the price of electricity. So the total price of the produced electricity began very high. And in this case, it's cheaper to buy from the Nordic power system, first of all, from the Sweden, and not to produce by themselves. So what is, for example, okay, I could show you in this side, we have a good curves, good graphics for the real
Consumption.
generation. Yes, this is Estonia. What we could see, yes, Estonia, they have as I said, thermal power plants, CHPPs, yes, with their own fuel. And here you could see that the main production, yes, is thermal, so by their CHPP units. For now, then we have a very high price for electricity.
Ooh.
No, it's not so high, but it is very high if we compare, for example, to the year of 2019. Yes.
This price for 1 megawatt or
Yes,
how
this
many?
price is for 1 megawatt. And you could see, or maybe some words about what we could see here. We could hear these Nordic and Latvian countries and zones for the electricity. We call them electricity nodes. Zone with the electricity price.
No.
Why? For example, for a small country like Latvia, Lithuania, and for example, Finland is big territory, big area, but the country is small. So we have the price for the whole country. But in countries, for example, like Sweden, when we have a lot of generation, yes, they are the area is divided into if I'm right, 5 zones or 4. I don't know. 1, 2, 3, yeah, 4 zones based on the generated units. For this region, they have a lot of generation, and that's why we separate this area like a separate zone. And in this case, yeah, as I said, what about the Estonia? Yes, for now, the price is high if you compare to the year 2019. And they could pay this tax for CO2 emission because this extra pay is nothing to the total price. For Lithuania, for example, the situation is the worst. For example, here you could see total consumption and total production. For now, you could see the
Importation.
Yeah, what they need, how much energy they need to purchase. And this situation is the same all the time because they can't produce so much of electricity. Why this situation? Because in the Soviet time, Lithuania has a nuclear reactor of a total power of 1 megawatt. And one of the how to say, I need to find the word. Okay. Okay. Okay, I'll call it a rule. It's one. The rule for Lithuania to join the European Union was to close this power reactor, nuclear power station. Yes, for now it is closed, and it means that Lithuania lose 1 megawatt of generation. And in this case, they still don't have any possibilities to cover this loss. That's why all the time we have a flow of electricity in this circuit to the Lithuania. One of the solution was to build this underwater cable from Sweden to Lithuania, yes, to cover this deficit. In this case, for our region, and maybe this solution is not so bad. Why? Because for this region we have such country as Sweden, with a very powerful economy and with very powerful generation. If we could see, if we compare, for example, for Latvia, yes, we need only 1 gigawatt, 1000 of megawatts electricity, yes. But for example, if we see what is happening in Sweden, yes, we see nuclear power. Okay, it is, for now it is quite small, but in potential it could be twice. No, they're just not producing, but they have a huge nuclear power. We have a huge hydropower. So for now they are producing, okay, where is total production? 20 gigawatts for now, but they could produce much more, 26 for example, as I know. So they are producing a lot of electricity and they are able to sell this electricity to neighbor countries. And for example, as if you know, this hydro and, for example, nuclear power is the cheapest one. Because hydro, you need just water, you need to buy any fossil fuel to produce electricity, and for the for hydro, and for nuclear, yes, if we compare, it is the cheapest one from all types of generation. Because if we produce electricity from water, and if we calculate, yes, the price for each megawatt, because this production need maintenance. Okay, water is free, but all types of maintenance, this construction of this hydropower plant and so on, at the end, the cheapest one still is the nuclear power. It is cheaper than the hydro. In this case, Sweden can sell this electricity to all neighbor countries. And for example, Norway and Denmark is using this potential. But Norway have a lot, you know, it's how to say, mountain country with a mountain rivers. Mountain rivers have a big kinetic potential. In this case, for Norway, yes, they produce a lot of hydro. You could see 21 gigawatt of hydro power. Yes, a lot of small rivers, but all of these rivers are mountain rivers with a lot of potential energy. Potential energy is transferred to the kinetic energy and to the electricity. Yes.
Yeah.
And as you know, Norway is a very small country. The population is very small, and in Norway there are no electricity consumers, because they have no big enterprise that could consume a lot of energy. For example, for Sweden, they have a lot of different enterprise, such for this metal, like an aluminium, iron, and so on. They have a lot of enterprise that consume a lot of electricity, but there is no such an enterprise in Norway, because Norway economy more based like fishing and gas and oil production. No, not the production, how extraction from the sea. So they're selling resource. Norway is selling resources and fishing. No, basically, with very small population. And the electricity, selling as electricity, is a very good opportunity for Norway to earn money. For Denmark, for example, Denmark has a huge potential with wind energy. We could see, the production, of course, is based on the wind speed. So if we have wind or we don't have wind, but we have a big potential. But wind energy is not a cheap energy. It's quite expensive, because if you imagine the expenses of a wind turbine, all these turbines, these underwater cables, and so on, this is quite expensive type of electricity generation. In this case, if we see the Denmark production and consumption, so it is importing. And if we see the schedule of this the balance of the Denmark power system, we could see that almost all the time they are importing. So they can't produce so much energy as they need. In this case, we can recap that for this region, yes, but we see this is the market area, yeah. This is economic model. Okay, we could see real power flows, but basically this is from the North Pole spot. This is market, this is pool, and we could see these real power flows with the prices. But okay, I'm just trying to be short, yes, but it's quite difficult, yes, because when you start to describe one thing, all other things go over. This is a market, and for example, Baltic countries are part of this Nordic power market. In this case, this Nordic power market, basically on the border countries, you see this flows to the Germany and Lithuania, yes. So if you open the homepage of the Nord Pool spot, you will see such countries as Poland and Germany as well, because they are border countries with the flows and they impact to the price. So yes, for now we have discussed that 3 Baltic countries don't have enough generation. Estonia for itself can produce enough because they have CHPPs. But in case that the price of electricity is high enough to pay taxes for the CO2. For Latvia, we have the main power of for Daugava River power plants, hydropower plants. We have 3 hydropower plants with a total power more than 1 gigawatt, but it depends on the water. Sorry?
What is a non-specified? It is solar?
Sorry?
There is a not specified power in Latvia. It is next to the thermal power plant.
Okay, if we discuss the structure of Latvian power, first of all, we have 3 power plants. The first one is Riga hydropower plant. Riga, okay. Maybe we could Riga hydropower plant. This how it looks like. This is in city Salaspils, next to Riga. Yeah, with a total power of 400 megawatts. So it is the last. Okay, we have 3 power plants on the Daugava River. The first one is the Pliaviņas has, the second one is Kegoma, and the third is Riga. Why the Riga is the last one? Because the BF, there's a difference from the upper level and the lower level is the smallest one, because it is close to the sea. And the biggest one, when this difference is the biggest, is Pliaviņas has in the middle of Latvia with a power of 800 megawatts. So the capacity is twice bigger. And the Kegoms is about 200. So the total capacity is about 1.5 gigawatts they could produce. But the production is based on the water and the water flow. If we have enough water, we could produce a lot of electricity. And we could sell this electricity to neighbor countries. If we don't have water, we can't produce enough. Okay, this is for hydro. About the thermal CHPPs. In Riga, for now, we have 2 CHPPs, Riga CHPP1 and Riga CHPP2.
Yeah.
CHPP1 is more designed to produce hot water and heat, because its electrical power is less than 200 megawatts. So it produces about, for example, 400 of megawatts of heat energy and less than 200 of electrical energy. So it is designed, for example, to cover this hot water domestic hot water consumption during this summer period. And the Riga CHPP2, for now, there are 2 power units of CHPP2. For total power is about 800 megawatts, so 400 for each. To be true, there are 3 units. The old one, Soviet, but for now, as I know, there is only one no, alive, one turbine, one steam turbine, and now it's in a reserve. So the new modern ones are 2 units with a power about 400 megawatts each. So total power is about 800, yes, and the heat power is less than the electrical power. So it is designed to produce more electrical power. So to cover, how to say, if we don't have water, we could run these CHPPs. But for CHPPs, for its technology, it's a problem what to do with the heat energy, because this production cycle is we produce it at once heat and electricity. Of course, we could produce electricity and put this heat to the atmosphere. But from the economical point of view, it's not very profitable, because we're not selling this heat, we're just wasting it. So for example, if we have very high electrical prices, yes, we can burn a gas, produce electricity, and don't sell the heat. But no, vice versa. So it depends on the, how to say, price of electricity, what we should to do. But yeah, with a total consumption, for example, about 1 gigawatt of electricity, we see that we could produce 1.5 by a hydro, and we could produce about 1 gigawatt with a CHPPs. So the installed power is enough to cover Latvian consumption. But if we see the total consumption and generation during the year, we have a deficit. So we produce less than we consume. Why? No, first of all, because it's cheaper to buy electricity from neighbor countries where they could produce it more cheap, like Sweden, because they have nuclear, they have hydro. Latvia don't have their own natural gas. We have to purchase gas to run CHPPs. And for example, if we talk about the heat consumption, because we are a Nordic country, we need a heat during the winter season. We have gas boilers. For example, the main consumer for this heat is Riga city, the capital, because a half of the population of Latvia lives in Riga. And in Riga, we have a district heating system.
Yeah.
So for this district heating, yes, we have gas boilers. And we could we could produce enough heat during the outdoor temperature -15 with only gas boilers. So we don't need to run CHPP to produce heat for this district heating system. So there is there is a concurrence. So who will sell the heat to the district heating system, CHPPs or gas boilers? So it depends on the price. If the gas boilers could provide the lower price, yes, for this utility company who provides for district system, yes, they will buy this heat from these gas boilers. If CHPPs could provide the lower price, so the utility company will buy from the CHPPs. So it depends on the situation. In this case, to run Riga CHPP, could be not profitable. It's more profitable to buy electricity and not to run. So yes, it's a market condition. It's quite complicated because yes, for the beginning, Riga CHPPs was developed to cover the basic heat consumption, and electricity production was like an additional product. So the main product is a heat, and electricity is like an additional product to cover the electricity consumption. But for now, when we have a market, it's quite complicated. And for example, this Latvenergo, the owner of these all big generators, made a lot of reconstructions for these Riga CHPPs to make it more flexible. For example, if I'm right, they have General Electric steam turbines and generators, so they are made a lot of no, together with General Electric support, a lot of reconstruction to make it more flexible. Because flexibility for CHPP is quite complicated due to the period of start and stop of CHPP. Because, you know, for CHPP, it's a question of temperature and pressure to produce the steam. And all these elements of CHPP don't like the fast increase of pressure and temperature because it destroys all the units. So they need a lot of time to slow reach these nominal parameters, yes, to run the CHPP. For example, it's about at least 5 hours you need to start the CHPP. And yes, to make it more flexible, it's quite complicated, yes, task. Yeah, to make it more flexible in the market condition. But to recap this situation, let's come back to this scheme. Yeah. Total, yes, all three Baltic states have this deficit of power.
And my question is near to the thermal, the next to the thermal, it was
Yes,
mentioned like not next to the thermal power,
yes. This one
not specified power.
not
Yeah, it is
specified.
solar.
Yes, yes. Because not specified, this is all small generators together.
Mm.
So you don't see solar here. Yes, you don't see solar.
Yeah.
Different small hydropower plants could be here as well, because this
Mhm.
hydro, it means this Riga, Daugava River, these three big power plants. So here not specified all other small generators. For example, we have such type of generation like a bio generation when so such type when we produce the biogas, for example. We have a lot, no, not a lot about, but I said about 100 small generators all over the countries in distributed network. Basically two types. The first one, they burn some bio like wood, no, wood chips, something like this, yes. And the second one, they are using the biogas. So, and then their power is up to several megawatts. Basically, they use modified these car engines, no track engines for to rotate generators. So they produce biogas. Biogas use like a fuel for these modified truck engines with 12, 20 cylinders, yes, and these exhaust engines produce rotate generators, and they produce electricity. We have a big support for some period of time for such type of generators because we call them green as well, because how to say, they use a fossil, but how to say, renewable fossil, and they had special pricing system for the electricity, because no, they have extra fees for their electricity, so they are selling produced electricity not based on the market price, but based on the government support. So they have a fixed price, very high fixed price for their production. So this business was quite profitable, because we have a government program for about 10 years with a fixed high price. So, and this was quite a good business to make this distribution network of small generators. So all these generators are here. But as I said, the power not more than several megawatts. So if we all of them unite, so here you could see, so the number is not so big. Okay, yes.
Yeah.
Let's come to the situation. Okay, so in this case, as I mentioned, yes, we have three states with a deficit. And it means that every time we need to buy electricity from our neighbor countries.
Yeah.
And we could add to this club with Finland as well, because Finland is a deficit country as well, no, historically. Historically, they have very close relationships with Russia, no, previously with Soviet Union, and they had a special agreement for the electricity purchase outside this Nordic market. So they have, okay, you have a law, yeah, that you need to buy an electricity here in the market. It's a European politic. But for several countries, they have additional extras. For example, for Finland, they could have an additional agreement with Russia, and they could purchase the electricity from Russia based on the agreement to Russia with a price, a very different price, not based on this market price of Nord Pool spot. And this was quite profitable for Finland because a constant flow of 1 gigawatt of electricity from Russia was all the time till the war in Ukraine. With the beginning of this war, yes, they dropped this electricity purchase from Russia. And in this case, without this flow from Russia, Finland is a deficit country as well. You can see, for example, for now, they're purchasing from Sweden here 1 gigawatt here and 1 gigawatt here. Of course, 1 gigawatt goes to the Estonia, Latvia, and Lithuania, but total they have inflow of 1 gigawatt. So they had inflow of 1 gigawatt from Russia with a very cheap electricity. And this was an extra support to a Finland industry. Because you understand, cheap electricity, it's a support to industry. Because electricity is in every thing you purchase. So, yes, and for now, this flow of 1 gigawatt come from Sweden. So, it means that Baltic states need electricity, Finland needs electricity, and Denmark needs electricity as well. All these countries are deficit, and only 2 countries like Norway and Sweden sell electricity to make this balance for these countries. But as I said, the decision was not to connect to the Nordic power, to synchronize to the Nordic power system, but to synchronize to the Central Union through the Poland. Come here through the Poland. As I said, this is a political decision, but let's discuss from the technical point of view how this could be implemented. First of all, to make this synchronization, we need a physical connection, to build physical lines to connect Lithuania to the Poland. And this was made, this interconnection to Poland was made. But there are some disadvantages of such a solution. First of all, as I said, we have a deficit from one hand, and we need to keep the balance on the other hand. And frequency, yeah, we should to be synchronized to this system. This means that if we, for example, have a deficit, we are not producing so much as we consume. In this case, the frequency is starting to decrease. So the frequency is this value that represents the balance. If we produce enough, the frequency is stable. If we are producing more, the frequency is rising. If you are producing less, frequency is decreasing. And the decrease of frequency is very dangerous. And the main thing to keep the power system work is to keep the frequency. And in this case, for example, if only here in the appendix of this huge network, we are starting to decrease, the frequency is starting to decrease. First of all, it's a rule, all other countries should support us to keep this frequency. So they should give us the power. In case they can't support us to keep all the system work, they will disconnect us. If they can't help, they disconnect. It is a rule. In this case, let's discuss how they could, for example, support us. We have a line connected to the Poland. But if we know the technical issue of the power flow, we could say that the distance from the real generator to the real consumer, maximum distance that the consumer could get the power from the generator, the real distance, not how to say the paper flow, but the real physical flow. What is the largest distance from the real generator to the consumer could be? The real distance is about 300 kilometers. The power is not going far than 300 kilometers from the generator. Why? No, it's a physics. The closer is the consumer, the closest consumer gets the power. The far from the generator you are, you can't.
There are losses.
Yeah, you can't get the power of this generator because the closest consumer will obtain this power. In this case, if we analyze the power generation structure of a Poland, we will find a very interesting thing. The main generation is in the west part of the Poland. And the transmission power network is in the west part of the Poland. The transmission line structure of West Poland is very poor. And in the west of the Poland, they don't have enough generation. So the east part of the Poland consumes power that is produced in the west part of the Poland. In this case, if we are connected to the east part of Poland, we can't get, in the case of trouble, a lot of electricity from Poland because Poland power network, west or east Poland power network is poor and they couldn't transmit a lot of power. In this case, no, if we will get troubles, we will not get power from here, from this region. The only countries that could give us energy is Sweden, because Norway, as you see, Norway is up to Sweden. So the electricity to come from Norway should come through the Sweden. So all in this case, so our balancing is based on the Sweden possibility to transmit electricity to Baltic states. This is quite complicated and quite not reliable. Why not reliable? No, first of all, because underwater cable is not the best from the reliability point of view, because it was standard for this interconnection between Lithuania and Sweden. It was an ABB underwater cable, and shutdown of this cable once a month. It's a typical shutdown of this cable due to technical reasons. different, of course, reasons, but the frequency of shutdown about once a month. And for example, if we lose about 700 megawatts of energy at once every month, it means that every time when this happens, when we lose this cable and the power 700 gigawatts, we are in a way of blackout, because it is impossible to balance for our three countries such a power of 700 megawatts. For now, we have special project to make, how to say, no, this new structure from the year 2025 possible. How we could deal with such a troubles? No, our technicians, based on, for example, Poland in one of the Poland universities investigation, decided to make main upgrades. First of all, they decided to put these battery storages in 3 countries with a total capacity of 100 megawatt hours, because from a battery you could obtain very quickly electricity and then very high amount. And the second one is this asynchronous compensators, this kinetic energy. What is it? Synchronous compensator. It is a big electrical machine which is just rotating. It's, how to say, a kinetic energy storage, type of kinetic energy storage. Because the main problem, in case when we have a big deficit at one moment, is to deal for the first seconds. How to deal with this deficit for the first second. And to deal for the first seconds is to use this kinetic energy of these asynchronous machines. So they, using their kinetic energy, could decrease the speed of this process in a power network. Next, we will discuss all these things for a power network, about what to do if we have deficit, what is the inertia of the power system, why do we need the inertia, how we use this inertia, but we will discuss this next. For now, it is like an introduction, yes? So, several special solutions, yes, to cover this unfortunate deficit. Because, as I mentioned, this deficit is quite dangerous, because if we will have the disbalance, if we have this deficit, we will have the frequency decrease, frequency drop. And if you have the frequency drop, we could have a blackout. Next, we will, for example, just for the knowledge, discuss the report of Italian blackout of the year 2003. This is quite interesting blackout of the whole Italy, how it was raised and why it happened. So I don't know when, but maybe next time or maybe later, but we will discuss with this blackout. First of all, for today, we have just an overview of the system.
Yeah.
Okay, so, but as I said in the beginning of today's lecture, our power system is the most reliable, maybe one of the most reliable in the world for now, when we are part of the Russia and Belarus. Why? Why? First of all, we have a very big reserve in transmission, because our network was built based on an idea of industrial progress, a very huge industrial progress. And this industrial progress stopped due to the end of the Soviet Union. But yeah, all this transmission system have a very huge reserve for power transmission. This is one. The second one is, as mentioned, this Volga River power plants. In case of trouble, they Volga River power plants can increase the production of electricity and cover all the consumption of three Baltic states. It is very easy. As you saw, for example, the Sweden, yes, the small Sweden, they have 4,000 megawatt of capacity of hydro capacity. The capacity of Volga River is almost the same, like in the whole Sweden. So in this case, yes, when we have such a powerful generators, very flexible generators connected to the power system with a very big reserve of a transmission, you will get a very reliable power network. So in this case, we could recap main issues for the reliable power network. A good transmission network, a lot of lines, because you could have only one, for example, one transmission line with a big reserve, but in case of trouble you lose this only one line and you will get nothing. You need a good network, a lot of parallel transmission lines with a good capacity reserve. The first one and the second one, a big reserve of the generated power. So it means that you, for a short period of time, so a very flexible and powerful generator that could increase production for a big amount for a short time to cover the uncertain deficit. If we have these two main issues, yes, we will get a very reliable power network. And for now, all these features are for free for us. So we are not, for example, paying to Russia for this possibility, nothing. We are if in case of trouble, we are just purchasing electricity from Russia and just paying for the electricity. And we are not paying for the possibility to get extra. If you understand the idea, because this system is still not till the end in the market condition. For now, of course, we have a political decision not to purchase electricity from Russia. But if we will see what is going for now, Russia is here, yeah, and you could see the flow. 200 here, 19 here. On the paper, yes, you will see the zero. On a bill, you will see, for example, zero. But physical flow exists. Because, as I said, the nearest consumers to the generator consume the electricity. If for example, for East consumers, the nearest generator is in Russia, in this case, it means that this consumer will get the electricity from Russia because the nearest generator is in Russia. No, it's like a law. The current flows to the direction where we have the smallest resistance. Distance of a line is a resistance. The nearest generator has the smallest resistance. In this case, we will get electricity from the nearest generator. Okay, so in this case, yeah, and here we should understand one more thing. In the market condition, you are paying for electricity, but also you should pay for the possibility to get electricity for such type of balancing. There is a special market which calls the balancing market. For example, okay, I have a power plant. And you say to me that in case of trouble, you need a possibility to get an electricity from me. I say, okay, no problem. I am not producing electricity. I am not selling electricity. I am just keeping this generator in case of trouble to give you electricity. But I'm not selling, I'm not getting the profit because I am keeping this generator for case of trouble. So it means that you should pay me to keep this generator in a reserve. And this is quite expensive. So for the new situation from the year 2025, this is a quite complicated task. For example, who and how will pay for this extra, for keeping extra power. For example, I need to mention, in Lithuania, there is a special, very interesting hydropower plant with the name Kronis. It was a part of the nuclear power plant, with idea that nuclear power plant is producing electricity on its nominal power all the time. But as you know, the consumption during the day and during the night is not the same. At the night, consumption drops, but the production is the same. What to do with this extra electricity at the night time? And the idea was to use this hydro pumping power plant of Kronis. So the idea was during the night time, when they have extra electricity from the nuclear power plant, they are pumping electricity up. And during the daytime, then they have the increase in consumption. They're using this electricity, this water, to produce electricity. So a storage pump, Kronis hydro power plant. This how this Kronis looks like. Here you could see a huge tubes, yes. Upper level, oh, you could see here. Okay, Kronis pumped storage hydroelectrical. There is the upper level, this is a lower level, yes. Then, no, it was designed like then they have electricity from this nuclear power plant. At the night time, they are pumping electricity here. And during the peak hours of the day, they're using this water to produce electricity. For now, nuclear power plant is closed, but we have market condition. We have electricity price deviation during the day. We have cheap electricity hours and we have high electricity price hours. So for now, this power plant is using cheap electricity hours to pump up the water, and the high electricity hours, they are using this water to produce electricity and selling electricity. This is the use of this hydropower plant. And one of the ideas of the Lithuanian guys is to use this Kronis pumped storage power plant for this balancing, to keep the water here like a reserve in the case of trouble. And they want to get, of course, extra fee for this keeping, and this extra fee is bigger than the market price of electricity because it's a business. So the balancing is a very specified type of this, how to say, power system operation. Okay, so this, okay, we discussed this system, we discussed how we connect, and okay, to recap this new interconnection to this unit. So this will be very complicated because, as I said, we have extra electricity from the north, and we can't get extra electricity from the system where we're going to connect due to the weak power network and due to the how to say,
flexible
generation location not in the East Poland but in the West Poland. In this case, as I said, we will not get extra electricity from here in case of trouble. The only way we could get electricity is from the north. And for example, one interesting thing, okay, not for example, sorry, I think we could close this this topic and start to the next one about the inertia of the power network. Yeah, what is it and how we could deal with this? Inertia, to be short, it's a speed of the process in a power system. In simple words, for example, we have a deficit, for example, power is not in a balance. We have, for example, a deficit of 100 megawatts. And inertia shows the speed of the frequency decrease. If we have a big inertia, so we have a very big power system. It means that the speed of decrease will be slow. If we have very small inertia, we have a very small power network, it means that speed of decrease of frequency will be high. So that's why inertia is very important, because inertia shows how much time do we have to deal with a problem. If we have a big inertia, we have a lot of time to deal with this problem. If we have small inertia, we don't have time. All the process will go very quick, and we will get in several seconds a blackout, for example. Yeah. So inertia is quite important. How we could get the inertia? What is inertia in physics? In physics, it's a kinetic energy of a big rotating metal piece, like it is a generator. A generator is an electrical machine, a big electrical machine, which one is rotating. This rotation is a kinetic energy. If we have a lot of generators, a lot of electrical machines, we have a lot of rotating metal with a big kinetic energy. This kinetic energy is an inertia. In this case, as I said, this is for this desynchronization, the one of thing how we could deal with this desynchronization is to use these synchronous compensators, because they're machines with this kinetic energy. Okay, and maybe a remark to this topic about the inertia. For example, all the renewables are not good for this power network stability and reliability, because they don't have an inertia. Because solar panel and inverter. Yeah, we have, for example, a generator, but this generator don't have any kinetic energy. And so, and this generator don't produce an inertia. The wind turbine as well, because, okay, turbine is rotating, but the electricity comes not from a turbine. The electricity comes from inverter. That's why there are a lot of papers how we could make an artificial inertia in an inverter to make it possible to add more renewable energy sources. Because if our, no, okay, in Europe, because it's more actual for Europe, or for example, for United States, for the West countries, the amount of renewables will increase. It means that the inertia of power system will decrease. And in this case, the reliability will decrease as well. How we can keep the reliability with the increase of the renewables? This, in this way, there is a solution, okay, theoretical solution, to build in each inverter an artificial inertia. Okay, but this was off top about this, how to say, renewables. Let's continue with this inertia. So as I said, inertia is a quite important thing for the power network balancing, for the power network reliability. And the first practical task, I think, will be to calculate the inertia, but I think we will do this all these practical things next. Today I'll try to deal with this theory, the introduction of the theory, because I think we will end in half an hour. It will be enough for us, 2 hours of this lecture. Okay.
Yeah.
So yeah, inertia. This is quite important. And the second one, what I want to start for today in theory is this frequency and frequency regulation. So the inertia is a parameter that makes all the that involves the speed of all this process. But the main parameter how to keep the power system is a frequency. How we could deal with this frequency? Okay, there is a dispatch center, special people, which task is to keep the power network in operation. How this is possible? No, first of all, they are planning the consumption and the generation. So we have a plan for the next day, for each hour of the consumption based on historical data, yeah, and we are planning the generation for each hour. Due to that, we need to sell and purchase electricity at the market. The main guys for all this process for now are sailors who sells electricity. No, sorry, not traders. Traders, yes, traders who sell this and buy this electricity. But dispatch center will say to the traders, is it possible or is it impossible what they are going to do? So dispatcher are technical guys, yes, who control what will happen in the power system. But the main guys for now are traders because they're earning money. And there is close how to say connection from these traders to the dispatcher to make all this work. So how dispatchers could provide this operation? First of all, they are planning all their maintenances, all this substation, transformers, line, disconnection, and so on, to keep this power flows. Because, for example, one of the most important reasons why the electricity price could increase in several zones is a problem of transmission. If we have any case of transmission line disconnection, it means that we could provide electricity from zone A to zone B. In this case, if we can't purchase electricity, it means that we will have a very high electricity price, yes, because the transmission line is disconnected. Yeah, so dispatcher center will monitor all the situation about this disconnection, about all these flows, and their task is to keep this balance. They have a special opportunity, yes, to use this special balancing power. So these extra generators, they could run, for example, because as you know, the real life is not a shadow. If you plan that in hour X, you will have the consumption of 100 megawatts, the real consumption could be 120 or 80 megawatts. You could plan, but you couldn't forecast the real consumption. In this case, you should change the generation for this hour as well. But you have agreement to purchase, for example, 80 from the market, but you need 100. So you need to find extra 20 megawatts to satisfy the consumption. In this case, we have intraday market and day-ahead market, yes? When we are planning our sales and buys for the next 24 hours, and when we have a special market, when we could buy extra or sell extra, because, for example, one country need extra 20 megawatts, but the nearest country don't, for example, don't need so much for this hour. In this extra market, they are trading these extra electricities to, how to say, to make the real consumption and generation feasible with this planet, as it was in the schedule. Yes, the task of the dispatcher. And how the dispatcher center could understand that everything is in balance, frequency. So they are controlling the frequency. And what to do if we have problems with frequency, if we have deviations of frequency, what to do? Okay, we could have two types of deviation, the increase of frequency and the decrease of frequency. In case of increase of frequency, this is not a problem because it means that we have overgeneration. Overgeneration could be, how to say, decreased very easily. You just cut a generation and you are in a balance. But when you have a decrease of frequency, it means that you need extra power. And this is quite complicated because extra power you need to find. Okay, so as I mentioned, you have the first solution is to use this balancing power. For example, balancing power for us is about 30 megawatts. So the dispatcher could call and use, I need to run this extra generation, yes, to cover this imbalance. But in case if this imbalance is more than we have in a balance, in a reserve, what to do? If we don't have enough balancing power, we could ask, yes, to get more power, as I said, in this special market, yes, when they are trading this balancing. Okay, but this could be impossible as well, as I said, due to transmission capacity limitation. For example, I would like to buy, but I can't because I don't have enough transmission capacity from the border countries. What to do? I used all my reserves from my power system. I can't purchase from the nearest countries because we have transmission limitations, or for example, our border country have several issues and they can't generate more. What to do in this case? The only way what we could do is to disconnect the consumer. Because if we will not make the balance, it means we will lose the power network. Will be a blackout. We need to balance the power network in any case. If we can't get any additional generation, it means we need to cut the consumption. In this case, there is a special automatic. It calls under frequency load shedding. And this automatic, it's fault automatic. So in normal operation, this automatic don't work. This automatic starts only in case of trouble, in case of big troubles. But this is the only way how we could keep the power system in case that we don't have enough generation, just to cut the consumption. And next week we will discuss this under frequency load shedding automation in details, and we'll try to calculate some tasks for this shedding. So I could recap. So for the next time, what do we have? We have practical tasks for this inertia. This will be the first. The second one will be for this under frequency load shedding.
Under?
Sorry?
Can you repeat again the second task?
Under frequency load shedding.
Okay.
Because I think I'll show you all the formulas and all the ideas next time, because it's more easy to make this calculation when you see all this. Because if I'll explain all the things for now, yes, You will forget all of
It
this
will be
for the next week. Yeah. So for now, as I said, I want to make it just so overview
overview.
of the system. This is of our course introduction. Okay. Yes. Two main tasks for the next week, and let's talk about this modeling, how we model the power system and how we make this concentrated power network. For this case, I'll use one book. This book is in Latvian and it is in internet. If you wish, you could go here, because I use only pictures from this book. But if you wish, where I have a chat, here is a chat. I can. This is the address of this home. This is our faculty small homepage with a
Yeah.
literature, and in the rear grammatas it is in Latvian book, and here we go. This book, and I want to show, I think it was in the first part. I'll open this first part. Okay. This two part is based to the control theory basics, but we'll go through these basics. I decided to go shortly through all the standard transfer functions, because it will be useful just to recap all the structures, but I need for now go. For now.
But I am the first student studying in English.
Yeah, but so I will not waste a lot of time for these transfer functions, but just to call the basic names and the idea why we will use these functions for the power network modeling. I think just I found I need this picture, because we'll start with and okay, I need this picture. Okay. It is in Latvian, but it is very easy. I'll try to explain. So let's discuss the power network in a concentrate point of view. So as I said, what is a concentration? When we try to imagine all the generators like a one big unit, and the same with the consumers, all the consumers like one big united consumer. We are trying to simplify as possible the power system. In this case, we could use this scheme. What is here in this scheme? I'll call you the each model. This one is a generator.
Turbine.
Which produce electricity. How generator could produce electricity? From a steam turbine. So this one is a steam turbine. How we could control a steam? We could control the valve. How much steam we flow to the turbine. So this one is the valve. This one is the steam. So steam goes through the valve to the turbine to rotate the generator. And this is the rotation regulator. It's a regulation of the rotation. So in this scheme, if we need to produce the correct amount of power, we need to deliver the right amount of steam to the turbine. And this is a structure. So we have a steam production. We are controlling, using this module, the valve to deliver the steam to the turbine, and turbine rotate generator to produce electricity. So this one is our power network. So it means that there is transmission and consumption. This is our united generator. This is the control scheme of this generator. So steam production, rotation control, valve control, turbine generator. This one is how to call it? It's like this is it's not so important, but it calls, but what do we do this? It's a transfer, like you know, when AC to DC transfer.
Converter.
Yeah, converter.
Stepped.
Yes, it's a converter. It just to convert the control signal, yes, to the physical implementation. It's just a converter, because here, yeah, there is a power system. We are get from here, from the power system to the this one is our control box. We get from here the frequency that shows the balance. This control says we are producing enough power or not enough, based on the frequency. And here the signal just from give more, give less, yes, goes here to the control. This is like a converter, yes, from a signal, because it's a signal and here is a physical implementation, yes. So using this scheme, we could represent the power system in the easiest way. So this is the easiest implementation. When we have generator, we have power system represented with the consumption. We have the main parameter of this power system, the frequency, control box, which controls this rotation and the steam flow via the valve. If we say we are not producing enough power, it says give more power. Give more power means give more steam. If we are producing too much power, this control box says produce less power. We are decreasing the steam flow to the turbine. This one, as I said, is the easiest way for the turbo generator. So if for our power network, the main generator is a turbo generators, CHPPs, we could use this scheme. For example, how we could upgrade this scheme based on the power network where we have several types of generator. For example, if we have more than half of turbo generators, it means that impact of the turbo generator is the main. We could simplify and use only one. If we have a big impact of the hydropower plants, we have modified the scheme and use in parallel the structure of a hydro generator. So we could use the scheme with two generators, concentrated generator for the steam turbines and for the hydro turbines. And the same we could use for the all renewables to represent with one more type of generators, which one will be represented with the inverter. Okay, but for the beginning, let's start with this turbo generator structure. And here I could, Okay, and yeah. And here, this scheme could be represented using the control theory like this. Here is a scheme representation with transfer functions like you see here. This structure is the same. This one, okay, let's start from this side. This one represents the power system and the consumption. This one represents the reaction of the power imbalance. This one represents the steam turbine. This one represents the valve, and this one represents the control box. So this one is transferred to this one. And next, we'll go through each of these transfer function. We'll see what is the name of this transfer function and why we represent each unit with how to say this transfer function. So our next step is to understand how we represent this, how we can make this, and from this, how to say, scheme, we'll understand why we need to calculate this inertia and we need to calculate this frequency. Okay, I think for today it's enough. I'll try to keep the lecture about 2 hours because 3 hours is too much from my experience for students in the evening.
Yeah.
Yeah. So next time prepare to calculate the tasks.
Okay.
I give you theory, I'll give you formulas, and I'll give you tasks to calculate. Because
Okay.
yes, based on this calculation, you will deal with your homework.
Okay.
So for homework,
Yeah,
for your homework, you will have the same tasks that we will discuss at the lecture time.
Okay.
You will not have any additional something for home calculation. I'll try to make it as simple as possible. So,
Okay.
yeah.
Yeah, definitely, Professor. We will discuss
Yeah, I think for November it will be enough for us once a week, but if I will see that we don't have not enough time, maybe in December we will have 2 lectures in a week. Yeah.
Okay.
Because for our plan is we have November, we have December, and we have January to get all the marks. So till the end of January, you should have all the marks, all 3 marks of practice and 2 subjects.
And about the quotation,
Sorry?
I mean, and about the